So welcome back to everybody. And as we started yesterday, we presented logistic regression, which is, a pretty simple way of getting started with classification problems. And the basic assumption we made, again, is that the data which we have, which in this case are given by discrete outputs, so typically it could be 0, 1, -1 or 1, yes, no, true, false, or you could have many more categories. So you're not limited to have a binary output. And typically you would have a continuous input, could be different sets of X values representing specific features. And then you want to classify whether you have a true, false case or whatever kind of case you want to classify. Now, the change from standard linear regression is that now we don't want to fit a continuous function, which in principle lives from -infinity to +infinity, but we actually want to represent or find a probability which now gives us a likelihood for a specific output, yes or no, as an example. So that's the big change, but the basic philosophy is more or less the same. We have a kind of overarching idea that there is either a function, a continuous function, or a probability distribution which describes our data. And logistic regression is also a method which we are going to use as a stepping stone towards, one, introduce the optimization technology, which we have to deal with, which means calculating gradients and finding the optimal parameters through the calculation of gradients numerically. And this is essentially the main topic today and tomorrow, together with a discussion of project number 1 tomorrow. And then the next thing is that it serves as an input to deep learning methods and neural networks. Actually, logistic regression is nothing but a neural network with no hidden layer, period. That's the way you can actually interpret this when we get into deep learning methods. And it's a very nice way to make the links here. So it allows us, this kind of stepping stone logistic regression is a widely used method. And if it works, if it does a good classification job, there is no point in using more advanced methods. And at the same time, it allows us to catch at least 2 birds with a stone. Now, just a quick, small reminder of things. When you scroll down this main GitHub site, you will find obviously the videos of the lectures, the links to the slides, and as well as the handwritten notes from every session which we have. And you will find a similar update today and tomorrow here. But let me quickly now just go back a little bit to what we did yesterday and look at the Jupyter notebooks for this week or for the day yesterday. And let me just change this so you see it properly. And as you see here, there's also a link to the lecture from yesterday, so you can actually revisit it. And one of the topics which we ended up with then, I'm just scrolling down a little bit. This is a typical data set, which in this case deals with heart disease, and the data are ordered according to age groups. And this is actually a data file which you can access in the folder, on the GitHub folder. It's called CH data. It's actually coronary heart disease. And the data here is actually data which I made up. And just assuming that the older you get, the higher the likelihood it is to get a heart attack. So the data here just manually made by me, but this is a typical case. So 0 means no coronary heart disease, and you can see as a function of age. And it's not so different from what you might actually expect from real life observations. And the typical thing which you end up with here is that clearly you could actually make a linear regression fit where you could have a line which goes straight through here. And then you would say if the value is larger than 0.5, then you have a heart disease, and if not, you do not have. However, if you now plot things in terms of the mean value, what you would get is something like this. And that is something which motivates the introduction of this sigmoid function, which we discussed yesterday. So what we are looking after is rather to have a function which lives between 0 and 1 in this particular case. And we can use that one to predict whether we have a heart disease or not, or whether we would default on the credit card debt or not, as we discussed yesterday, or any other type of binary classification problem. So what we looked at was essentially a binary classification problem. And what we did then was to introduce this logistic function. So this is one way of defining this probability distribution. And there are many, many such functions. And these functions, they actually do play an important role when we later are going to discuss neural networks, because these functions are used as activation functions for the different nodes. And you see also one problem here, which is going to be very important for neural networks and the calculations of gradients. So the gradient, when we now are going to evaluate and find the optimal parameters of a given model, will depend on the derivative of this function. And you see now that this function here, when you now extend this to larger values of z here, you see now it gets flatter and flatter. So this is gonna, at the end, it's gonna look like, as we Norwegian says, Denmark seen from the sea. Or maybe we could say the Netherlands seen from the sea. Actually, the Netherlands are below the sea level. Perhaps that's the reason why the Dutch people are the tallest people in the world, right? There has to be a reason for that. They actually are. They are the people with the highest, I mean, they're on average the tallest people in the world. And there's a funny thing, by the way. I live in Michigan half a year, and there is a Dutch settlement in the western part of Lake Michigan. And that's also part, I think that settlement, or the people which settled that came from the Netherlands, and they are still the tallest people in the US. It's quite interesting. Maybe it's because the country is below sea level. I don't know why. You could replace that with a step function. And you have also the tan H function. So these are all functions which could play the role of such a probability. Now, there's one thing, so I'm anticipating some of the discussions which are to come. If you look at like the step function, one of the problems here is you have a discontinuity. So when you're calculating derivatives, you're going to get a discontinuity. And many people handle that by just putting the value to 0, which is mathematically not very correct, but that's a way to circumvent numerical problems. So many of these functions which you look after, you want them to be continuous and to have continuous derivatives. So these are typical functions which are then used in this kind of process. And yesterday we looked at the logistic regression with this sigmoid function, and then we simply evaluated the probability for having output 1, which we gave by this function, which had as argument beta 0 and beta 1, just 2 arguments. And then, since we only have 2 events, then the other event has to be 1 minus this probability here, period. And then we use the maximum likelihood, and we calculate the log of the maximum likelihood in order to define the cost function. And that's the function which we optimize. So, when we did the derivatives, this is basically what we went through yesterday. We have a closed form expression for the first derivative and the second derivative. This is going to be a semi-positive definite matrix. And the problem which we face now is that we have derivatives which depend in a nonlinear way on the unknown parameter beta. Because beta enters this variable p, which is a probability, which we have defined through the sigmoid function in this specific case. So that means that we have a nonlinear problem. And if you just scroll down here, you will see other cases here. We're not going to look at this yet. But what happens then is that we are going to solve this. And as we did yesterday, we did a Taylor expansion around the optimal value. And when you do a Taylor expansion around the optimal value, and you truncate your Taylor expansion at the level of the second derivative, we end up with this equation here. So this equation here involves the second derivative, which is this quantity, with the approach we did with logistic regression. This is a matrix, which we call the Hessian matrix. And then we have the gradient here. And as we said yesterday, the thing we want to avoid is actually to calculate the Hessian matrix when it's inverse, because these iterations are iterations which we will keep doing again and again and again. And typically you would do hundreds of such iterations. And if you have thousands of parameters, you can easily do the mathematics and see how many times you need to invert that matrix. And that matrix is calculated at the value from the previous iteration. So this is the typical bottleneck which we face in all of machine learning. So the optimization part is the true bottleneck. And basically what we did yesterday, when we made the Taylor expansion and truncated at the level of the second derivative, which is at the level of this Hessian matrix, then we recover this equation here, and that gives us Newton-Raphson's method, period. So we are actually dealing with a Taylor expansion around the optimal values. So what I'm going to do first today is to go back to the whiteboard, and we are going to do some more analytical exercises with the Taylor expansions. And we are going to look at a method then, which is called steepest descent, which many of you may have heard of. So all these methods involve the evaluation of either the Hessian matrix or some matrix vector product. And what we saw yesterday is that the standard approach is actually to replace this quantity here with a parameter. And that parameter is called the learning rate. And we can treat that in many, many different ways. So the simplest brute force way is just to put it equal to constant and just play around with that. And then many people do actually, because that's cheaper numerically and computationally, to actually have a grid of learning rates and simply run the calculations with that and find, for instance, the optimal mean squared error with a preset values of learning rates. Or you could do a grid search and find the optimal learning rate, which gives you the best score for that specific data set. So this becomes an important parameter in machine learning, and it's simply called the learning rate. So in order to build up the intuition about methods which allow us to change this constant in an adaptive way, we need to look at methods like the steepest descent and some other simple mathematical manipulations. So just keep in mind that the mathematics we did yesterday was a Taylor expansion around the optimal value beta, where we have to deal with vectors and matrices. They're no longer scalars. So that's the main complications. And that leads to this equation here where the beta, the bolded quantities, are actually vectors, unless you just have one parameter beta, because then it's just a scalar. And then you're back to one dimension. Okay, so what I'm going to do now is just to switch back to the whiteboard and remind you a little bit of the things which we did yesterday. Let me just bring this down. And everybody can see well, okay? So the thing which we did yesterday was actually to make a Taylor expansion of this learning rate and of the cost function C of beta around the optimal value, where actually what we did was to replace the optimal parameter beta hat with just beta, just for notational simplicity. And what we had then was a Taylor expansion of C beta, where we now have a constant part which is evaluated at the learning rate, no, at the parameter beta in the previous iteration. And then we got now terms which went like a beta, we had the gradient transpose, since these are vectors, at the iteration n multiplied with beta minus beta iteration n. And then we had plus 1/2, and we should put an approximation sign here because we stop actually at the second derivative. And then we have a beta minus this beta iteration n transpose multiplied with a Hessian matrix evaluated at iteration n. So we're actually calculating all the second derivatives at that iteration. And this is then multiplied with beta minus beta of n here. The betas are vectors now. And then when we did that, we would then find that the optimal beta is given by the beta from the previous iteration minus the inverse of this matrix at the iteration n and multiplied with a gradient at iteration n. And now I'm just going to write it like this. So that means that the Hessian matrix and the gradient are evaluated at the value of beta for iteration n. And what we did then yesterday was simply to replace this with a parameter, which we call the learning rate. So what we're going to see today is a approach where we're going to start with a constant learning rate, and then gradually we're going to replace that with adaptive learning rates. The adaptive learning rates, which have a simple recipe for changing it, to a recipe where you have information about the gradients. So what I wanted to do now is to just play around a little bit with this Taylor expansion, and then we're going to see how we can extract some information about this learning rate. And this is going to serve as a stepping stone towards the steepest descent method. But everything I'm going to do now is going to involve you being able to calculate the Hessian matrix. And that clearly puts a limit to the practicality or the numerical, the numerical efficiency of the algorithms, because we need to calculate a matrix. And this matrix involves second derivatives. Okay, so the one thing we could do now, so what we found, if we now look at this beta, so we can rewrite this and we write it out as a beta minus a gamma. So now I assume that I have a constant, and then I multiply this with n. And then I just expand the cost function. So I do a Taylor expansion again with the with this value. So I expand around this value. So this is my optimal value. So I'm expanding around this specific value. So that clearly gives me just a constant. So I can evaluate the cost function at this value. And then I have a minus, and then I get this gamma. So just putting in back into the expressions, g times g. And now I'm a little bit sloppy with the indices here. So soon now I'm going to drop the superscript n. So let me just drop that immediately. So the g here is evaluated at iteration n. And this contains now plus 1/2. And then I have gamma squared. And then I have my g transposed multiplied with a Hessian matrix times g. And then this goes higher with higher terms. So remember now that the second derivative is the Hessian matrix. And what you could do now is to ask yourself, what is the optimal value of gamma? So we would truncate at gamma squared. And then we ask ourselves, what is the optimal value of gamma, which now gives the best cost function or parameters beta. So what we want now is to find the optimal gamma. And then we would take the derivative of this cost function with respect to gamma. And the first quantity, which we have here, the C of beta of n, is just a constant. So that doesn't depend on gamma. And that means that we are left with just two terms. We have one, which is given by gamma, and then gamma squared. So it's pretty easy to do the mathematics. And we find then that when we want this to be 0, we find then that gamma is equal to G times G transpose divided by G transpose times H. times G. So I've skipped the superscript or subscript n here. So everything here is evaluated at iteration n. Now, what we have here is an analytical expression for this gamma, but it all hinges on us being able to calculate the Hessian matrix, as you can see. However, this can give us some kind of insights. So one thing you see immediately, if you think of a Taylor expansion, one of the things you see immediately, so we will run into problems in a Taylor expansion if the denominator here, expansion problems, when this G transpose times H times G is larger than G transpose times G. So we would typically like these terms to become smaller and smaller. So one thing you could assume now, and this is a little bit related to numerical methods for finding the optimal values. If you now assume that this G is an eigenvector of the Hessian matrix. So assume G is an eigenvector of H. So that what we would have then is H times G is given by a lambda times G. And then we also assume that G transpose times G is equal to 1. So this is a orthonormal eigenvector basis. So these are just assumptions I'm making. Then what we see now is that gamma is going to be equal 1 over lambda. And then we know that the smallest step size is then given by step size given by lambda is equal to 1 divided by lambda max, the maximum eigenvalue. And the largest step size or learning rate, so let's put it like this, the largest learning rate or step size. So these are normally used as equivalent words, or step size, given by gamma is equal to 1 divided by lambda min here. So within this domain, you should then be able to get something which can converge. Now, you can actually show mathematically here. So we can show, and this is based on analysis using the singular value decomposition. So I'm just stating it now. So we can show that this gamma should be smaller than 2 divided by lambda max, where lambda max is the eigenvalue of the Hessian matrix. So lambda is eigenvalue of H. And the convergence rate of these methods depends on the relation, the ratio between the maximum eigenvalue and the minimum eigenvalue. So the larger the gap between the maximum and the minimum eigenvalue, the slower you will converge towards the minimum. So these are statements which I'm just listing here, but they're actually going to be a little bit useful when we now are going to run our first codes here. So if you can diagonalize this Hessian matrix, then you get a kind of a guideline on the size of the learning rate. Now, there are many methods which try to approximate the Hessian matrix. So if you go into the literature, you will often hear about a method which is called Broyden, Goldfarber, Fletcher, etc. You will often see the acronym BFG something. I don't remember all the names of the authors, but these are so-called quasi-Newton methods where you try by extrapolation to estimate the Hessian without calculating the Hessian. So these are extremely valuable methods, but one of the reasons why I mention these methods is that they all these methods, in one way or the other one, they rely on you being able to calculate something related to the Hessian matrix. So just keep in mind that if you look back at the main problem which we have, which is expressed here. For many, many applications, the dimensionality of this Hessian matrix is going to be too large for us being able to implement it in practical ways. And that means that we normally replace that with constants or different approaches to evaluate this specific learning rate, either with information about the gradients or not. So the methods which we are going to encounter a little bit later, they deal with ways by which we can try to accommodate some information about the gradients in this ratio here. So before we move on, I actually wanted to present to you a method which is also widely used in this kind of searches, as long as the matrix dimensionality is not too big. And one of these methods is called steepest descent. So it's not gradient descent. The simple gradient descent means that you take the expression which we have here and just replace gamma with a constant. Now, the steepest gradient descent, and which is the simplest way of approaching a method like the conjugate gradient descent, which many of you may have heard of, they are all methods which try to evaluate this gamma in terms of matrix relations of this type here. So if you can afford computationally to calculate quantities like this, then you should think of doing that. However, in most cases, when you deal with deep learning methods, you can just forget about it because you're going to have zillions of parameters. And then there's no way you can calculate these quantities in an efficient way in a reasonable amount of time and with your computational resources. So what I wanted just to do before we move on is to say something about the steepest descent, which is another algorithm which you may encounter. So if we now look at the steepest descent as an intermediate step here, no, steepest descent, not steepest descent, but steepest descent. So what we said yesterday is that the problem we are dealing with is us finding the zeros over the optimal points for this function f of x, which can be written out in terms of this matrix vector relation here, times x transpose times b. So A is something we can calculate, and which in our case is the Hessian matrix, and B plays the role of the gradient, which we have in the derivative of the cost function. So what we want then, if we take d of f with respect to x, the derivative, and want to have that to 0, that simply gives us a well-known linear algebra problem, which is matrix A times vector x equal a known vector b. So this gives us A times x is equal to b. So this kind of second order problems are actually at the root of many of these optimization problems. So for us, this is actually a Taylor expansion of the cost function where we stop at the order of the second derivative. So what's common to do then is to define a residual which we just call for R, which is b minus a times x. And normally you would then start with a guess for these values, and you have a solution when R is equal to 0. So you would typically start with a guess. For x, which will typically be some x0. It could actually be 0. So how many of you have seen the derivation of the steepest descent method? It's a pretty common method in linear algebra. Now, if you look at what we have here, if you look at this expression here, there is a very interesting statement. So if this matrix A is semi-positive definite, which is the case in linear regression and in logistic regression. If the matrix A has these mathematical properties that the eigenvalues are larger or equal than 0, then this kind of iterative process will converge to the exact solution irrespective of starting point x0. So you can actually put x0 equal to 0, and then you will start iterating, and it will converge to the exact solution as long as the matrix A is a semi-positive matrix, semi-positive definite matrix. So these are very important statements, and if you can show that the matrix has these properties, and we've seen that this is the case in linear regression when we did the singular value decomposition, that the eigenvalues are all larger than 0, then this will actually converge irrespective of starting point. That's a very powerful statement for many of these iterative methods. This is also one of these many of these hidden gems in linear algebra, which you often don't hear about. Okay, so what you would have then, if you start with that, you would have the first value, R0, which is given by minus A times x0 plus B. And you could, if you put R x0 equal to 0, then R0 is simply equal to the vector B, which is normally known. This is a known quantity. So in general, what you have is an R of k plus 1. You do k plus 1 iteration, which is equal to B minus A times x of k plus 1. We're also going to assume that there is a general relation for x, which is now given in terms of the previous value, plus some alpha of k times this residual R of k. So x changes, and you can see that from the relation which you have here. So x changes according to a specific recipe where you have a constant alpha k multiplied with this R of k. And then the whole thing now is actually, how do we find alpha of k and R of k? So if we now look at this R of k plus 1, we can rewrite it in terms of this new definition which we have here. So if you look at this definition here, we can now rewrite R of k plus 1 as B minus A times x of k plus alpha of k times R of k. And that is given by B minus A times x of k minus, and then we have alpha of k times A times R of k. And then we know that this quantity here is nothing but R of k. So what we have then is just R of k minus alpha of k, and then times A times R of k. Now, what we want is the following. We want that R of k plus 1, if it converges, should be equal to 0. That's the convergence criterion which we have defined. Because when we have reached the correct solution, the residual has to go to 0. Because that sounds reasonable, right? I mean, nobody would argue against that. So with that, what I can do now, if we now assume that Rk plus 1 is 0, I simply multiply from the left with Rk transposed. So I would now have, I multiply with Rk transposed, Rk plus 1. We have assumed that Rk plus 1 is 0, so we should get 0. So this is given by Rk transposed times Rk minus alpha of k of Rk transpose times A times R of k. And that leads to alpha of k is equal to Rk transpose times R of k, and Rk transpose times A and Rk. This concludes actually the recipe for steepest descent. So the value of x, which we are looking after, is now given by x of k plus alpha of k, which we have calculated, multiplied with this vector r of k, which represents the residual. So we can interpret this r of k as actually, when we go back to the cost function, this r of k is nothing but the gradient in our equation for the parameters beta. So this plays the role, when we now go back to the cost function, plays the role of the gradient g, which was calculated at beta at n. So remember now that in our case, what we have is beta of k plus 1 is equal to beta of k minus a parameter gamma of k, and then multiplied with this gradient g of k. So this is the expression which we are looking at in more explicit ways. However, what you see here is that everything depends on you being able to calculate the Hessian matrix. So in our case, H is equal to the Hessian matrix. So you see now, if R of k is a gradient, this expression which you see up here is the same expression which we derived here from the Taylor expansion. So it's the same expression which you see here. So when we did that Taylor expansion in the previous case, around the optimal value, where we made this specific assumption, this gamma is now the parameter alpha of k from steepest descent, which is one of these famous algorithms. Now, steepest descent is a little bit inefficient algorithm because it tends to have the same kind of rate in all directions. And the method which normally is a better one is called the conjugate gradient method. But this method as well relies on us being able to evaluate the Hessian matrix. So everything I've showed you till now means that you should be able in one way or the other one to calculate a quantity like this. If we go down to the steepest descent method, which is one of the popular methods for finding the roots, we have a general expression here, but where A is the Hessian and R plays the role of the gradient. So all these methods are very nice. And if you can calculate the Hessian matrix, if your matrix is not very large, let's say you have something like a dimensionality of 10 features, so the matrix of dimensionality 10 times 10, then this can be doable. And you will often see then in many implementations. So if we go back to the Jupyter notebook, and there is a data set here, or an example which we have in the Jupyter notebook, on where we use the Wisconsin cancer data. And one of the things you will see then, when we call the logistic regression function, so this is the Wisconsin cancer data, and this is already included in a library like scikit-learn. So we would simply import logistic regression, as you can see here. You load the breast cancer data. So this is a data set with something like 500 entries of patients, and it has 30 features, which means that you have something like features like the size of the tumor, the color of it, the thickness, the perimeter, etc., etc. And when you now want to run it, you would typically then split the data into train and test, as we've been discussing. And the data is already set up for you, so you don't need to read it in, pay attention to the way the file is set up, and so on, or the input data. But now you see that when we call logistic regression, I'm calling a solver here. So this solver is a quasi-Newton methods where you try to evaluate the Hessian matrix. And I will show you examples later on how fast things can go when you have the Hessian matrix. So this LBFGS stands for, I think B stands for Broyden, F stands for Fletcher, and then I've forgotten the other three names. I'm sorry for that. I've been reading this algorithm. I know how the algorithm goes, and I've seen the name of the authors zillions of times, but I only remember 2 of them. I don't know why. I can't explain it. Okay, but then this is the way you would set it up with scikit-learn. And you see now you split the data. You see the accuracy with logistic regression is 94%, which is not so bad. You can do other things here. You can look at the correlation matrix and so on, but we are not going to look at that now. So you have other ways of setting up and plotting the data. So let me just show one of them because we're coming back to some of the other ones. So what you do here is no longer to calculate the mean squared error as an accuracy score, but you plot something which is called the accuracy, which simply counts the number of cases you classified correctly. So if you classify all events correctly, your accuracy score is 1. It's 100 divided by 100 if you have 100 cases. So 0.94, 0.98 means that you classify correctly 94% or 98% and so on. And there is a quantity, before we take a break now, which is called the confusion matrix. Have you heard of that? So this classifies true positive, true negative, which is what we want to classify correctly. But then you can have a false alarm, like false positive or false negative. That's a very nice way of actually presenting your data. Because some of the data may be a little bit skewed. There may be more true positives than true false. So this 500 data, this cancer data is pretty balanced. So the number of malignant tumors and benign tumors is roughly 50-50. But you can have data sets which are more skewed. And then you have less data to reproduce when it comes to true positive or true negative, right? So this is something you would have to pay attention to if your data is a little bit skewed when it comes to the type of outputs. There is in scikit-learn again, there is a very nice package which is called metrics, and here there's this confusion matrix. And if we plot that, you will see something like this. And then we can stop after that. Actually, you will see with, oops. Oh, I forgot actually to run the previous case here. Sorry. Yeah. So the confusion matrix, no, what did I do here? Did I do something? Then there's a good time to take a break actually, because I probably actually did some editing here, which changed some of it. But I could show you another property which you can see here with scikit-learn, where you can plot the frequency of the data, which is very useful. So you can see something like the mean radius is something which is very useful for a pathologist to look at, because you can see now that the benign cases and the non-benign cases are well separated. So if you go to a feature like the mean radius, and obviously the mean perimeter is correlated with the mean radius, right? So these are features which allow you to distinguish pretty well between a benign and not benign tumor. But then you have other ones like the mean texture here, which are more difficult. You would have mean fractal dimensions. I mean, some of these things I have no idea what they mean. So there you would have to go to a pathologist and actually discern what this actually means. And this kind of scans are extremely useful. So I don't know if you're familiar with the Chinese company Alibaba, which is the equivalent of Google in China. They have developed very efficient algorithms to identify tumors, because China has the problem that the number of doctors per inhabitant is much lower than what we have in the Western world, which means again that if a pathologist runs through the scans, it takes often 1 to 2 days to run through the scans manually. So if you can then flag those cases which are a little bit dubious, then the pathologist can use all of her insight about the problem and then analyze the tumors or that specific cases which are flagged as more difficult for the machine learning algorithm to classify. So these are extremely useful tools. And then I'm going to try to fix that thing. It's not so important because we will meet it later. But let me put the recording on break here, and then we take a small break. So before the break, I wanted to show you the way you can display the metrics from a logistic regression calculation. And one of these functions is the one which we call plot confusion matrix. And this is a pretty popular way of presenting the data, especially when you have a binary class. And this is a normalized confusion matrix. And the first one is actually true positive. And I actually don't remember whether they classify positive as a malignant tumor or benign tumor. I think they actually classify a malignant tumor as a positive one, which I wouldn't call a positive. So you can see now you can split it, so true positive and true negative. So you classify correctly 93% of the true negative ones and 96% of the true positive ones. And then you have misclassified events here, which will be true, false positive and false negative, which you can think of as a kind of false alarm. So this is one way to easily convey the information to people, actually. So next time you go to a party, this is something you can show to your friends. Maybe it's a reason why nobody invites me to parties anymore. Okay, let's now switch to the topic this week. And now the topic for today, which is more about the optimization itself. So what I want to do now is to show you how you can implement the simplest gradient descent on the problems which we looked at earlier. And in the slides here, you will find some more general kind of information and also links to textbooks. So we have this textbook by Goodfellow et al., which you also have access to online. I don't know if you had time to look into it, but it's a very good one. It's normally the textbook, which it's a kind of standard textbook in machine learning now. And if you go to their website, you can actually find chapter by chapter. So in chapter 8 here, they actually do discuss a lot of the optimization method for training methods. And you will see many of the kind of arguments which we've gone through being exposed there as well. And what you will encounter, and which disappoints many people, is that we are going to meet tons of parameters. So we are going to introduce new parameters. We've introduced the learning rate, that becomes a new parameter. And then how to efficiently find the best learning rate, etc., are things which we're going to discuss now. But anyway, this is a pretty good textbook, which I normally recommend. And this is just a repeat of what we've gone through. There's also some material about the Jacobian, finding about the properties of convex function, etc. You can just look at this as background material and just take a look at it. There's a repetition of the standard steepest descent, which we went through now. So you will find the same expressions which we looked at earlier. There's a simple example here, but this is not the thing which is going to interest us in greater detail. There's also derivation of the conjugate gradient method. But if we now look at a simple case and how we can now implement the gradient descent, where we have just a constant learning rate. So if you now take a data set, which I simply define in terms of a random number, a uniform distribution multiplied by 2. So these are numbers between 0 and 2. And then I simply have a output y, which is given by these x's multiplied by 3. There's an intercept, and then some random noise, which is normally distributed. And if we now look at the example here, we are going to make a fit where our y of I is given by beta 0 plus beta 1 times x of I. I keep the intercept, so that means that the design matrix is simply given by this. We have 100 points, and this is a basic case. This is now the cost function. It's pretty easy just to spell it out, simple algebra. And then we have the derivative here. So we have the derivative with respect to beta 0 and beta 1. And this is something which defines our gradient, which we can write in a more compact way like this. Now, what you see now for standard linear regression is that you have a matrix times a matrix. So obviously that, when you evaluate it, this is just a baby case with 100 times 100, so it's 100 points. So the multiplications we need to do is 100 squared. And plus multiply with a vector beta, which now has length 2. So x transpose times x becomes a matrix of dimensionality 2 times 2, because we have only 2 features, the intercept and the first exponent. And that means that the calculation of this quantity here is not that difficult numerically. It is not computationally intensive. But you see clearly, if you have thousands of data points, or tens of thousands, or hundreds of thousands, this is going to be computationally expensive. And this is the reason I mentioned this is that this is going to motivate what we call stochastic gradient descent with batches. So where we, instead of running over the whole data set, as you can see here, we're actually going to run over just a limited number of data points. But we will run through the whole data set. We're going to split them in smaller batches. And that means that the computational cost for the matrix-matrix multiplication is going to be lower in total. Again, we can calculate the Hessian matrix, which in our case is 2 divided by n, x transpose times x. So we have the derivatives here. And in this specific case, it's rather straightforward to calculate these derivatives with respect to the different parameters. And you can see these derivatives are easily evaluated. So you have nice expressions for it. So one of the things we're going to do in the code here is actually to implement the standard gradient descent, which is this. So we have a fixed learning rate multiplied with a gradient. And if you now look at the code here, I'm just setting up the data points. I'm setting up my design matrix. I evaluate the Hessian matrix, as you can see, and I also diagonalize the Hessian matrix. So you remember from the previous hour that we said that the optimal learning rate can be defined by the eigenvalues of the Hessian matrix, and the best or the eigenvalues or the learning rate can then be defined by the smallest or largest eigenvalue. So what I'm doing here, I'm choosing the smallest learning rate in terms of the largest eigenvalue. So here I'm actually setting the learning rate to be given by the eigenvalues of the Hessian matrix. So this is a pretty easy case to calculate for linear regression. And here I have a very stupid code. So I'm not putting in a convergence criterion. So here you should actually have had while it hasn't converged, and you would have a smaller number of iterations actually, not 1,000. So the typical number which people tend to use is between 30 and 100. But in this case, I'm just doing a very brute force calculation. But here there should be a stopping criterion, which says that if the gradient, all these parameters beta don't change more than a specific quantity from one iteration to the next one, you should stop. But as I said, this is just a stupid program which I wrote with not too much, how to say, refinements, not too many refinements. But you see now that I'm calculating the gradient. And here as well, I'm calculating the gradient in just by doing a matrix-matrix multiplication. And then multiply with a vector, and then it's multiplied with a vector y here. So this is just the analytical expression for the gradient. Now, a little bit later, that means tomorrow, I'm going to show you how you can do this without calculating the gradient yourself. Have you heard about automatic differentiation? So how many have heard of that? Okay, so when you ask me about the best algorithms ever, I have singular value decomposition, and then an equivalent algorithm for me is automatic differentiation. This is really the closest you get to painless dentistry. So the whatever that is. But the thing is that with automatic differentiation, you don't need to calculate the derivatives. You're actually going to use the chain rules together with the functions like exponentials, cosines, and sines to calculate derivatives to numerical precision. I'm going to show you tomorrow how you can use automatic differentiation, because that really saves the day for you, especially if you have complicated functions. And when we are dealing with neural networks, automatic differentiation. In Python, it's included by a library called AutoGrad. And later this has been updated to JAX, J-A-X, which also includes efficient GPU usage and high performance computing. That's an incredible library, which I really recommend using. So especially when you deal with deep learning, where you're calculating the gradients of complicated cost functions, automatic differentiation is really what saves the day for you. So I do computational quantum mechanics, and I've been using neural networks to solve Schrödinger's equation. And there we actually deal with automatic differentiation extensively. And that really automatizes calculations of derivatives. So, and there are two ways of doing that. There's something which is called the forward mode, and then the reverse mode. And you are going to encounter, after in the new year, something which is called the back propagation algorithm for neural networks, which is the way you evaluate gradients. And the back propagation is the same as reverse mode in automatic differentiation. So there's a very nice connection with one of the perhaps really hidden gems in numerical mathematics, automatic differentiation. That's really, you're probably used to calculate finite differences, right? So you take a 3-point formula, and then you take the difference between the function values. You have a step size, and then you let the step size become smaller and smaller. Then you accumulate numerical errors. At a certain point, it just breaks down. If you use that one to calculate the third derivative of e to the x, a simple function, you will fail miserably. Really, I guarantee you. If you use automatic differentiation, you will get the precise result to numerical precision. Okay, this is a little bit propaganda. But this is what I'm doing here is actually to calculate the gradients. And later we're going to replace that with automatic differentiation. But if you look, this is actually the simplest possible way we can implement things. And if you now look at the gradient descent, so this is the intercept and this is the slope. And you see that these are the eigenvalues of the Hessian matrix. These are the results by matrix inversion. And this is a result by my gradient. Now, suppose now that, and you see that the largest eigenvalue is 4.4. There's another thing here which makes life easy. With linear regression, since it's called linear regression, there is no dependence on the unknown parameter beta in the Hessian matrix. So you can pre-calculate this and actually find the optimal parameter. So if you do linear regression, you can actually diagonalize the Hessian matrix once and for all. When you do logistic regression or any other method where you have a non-linear dependence on the unknown parameters beta, you would have to diagonalize your Hessian matrix every iteration. And diagonalization is an n-cubed floating point operation process. But here you see you get spot on. Now, suppose now I change this now. So what I could do now is to change this. So you saw the largest eigenvalue is 4.4. But let's now suppose I just put this one to 0.1. And let's see what happens then. It still converges. Let's just make the learning rate a little bit larger. Let's put it 0.5. And then it diverges. So what's going to happen then is that you are going to move towards the minimum, but then you're going to jump in and out with larger and larger jumps. And at the end, it just diverges. So this is a typical example where you've gone beyond that region, where gamma has to be smaller than 2 divided by the maximum eigenvalue. Then you could make this, you could say now, okay, let me be safe and let me make it as small as possible, right? This is another way of just circumventing that. And then you will see now, oh, you're not getting the same answer. What you could do is then, okay, let me just increase the number of iterations. If you are willing to spend a lot of time, you see now it's converging towards the right value. So in this simplicity which you see here, you see the basic message. And that is that the learning rate is something we have to live with in one way or the other one. And everything which comes now is a way to circumvent the full evaluation of the gradient and to circumvent a constant learning rate and calculating the Hessian matrix. This is all what it is about. In the examples here, you will also find a similar one when you use scikit-learn. This actually uses a stochastic gradient regressor. So this has done a stochastic gradient calculation for you. You can define a number of iterations. You can start with an initial learning rate. This actually does an adaptive learning rate. But since it's stochastic, in principle, you don't get the exact result because now you're calculating an expectation value of the gradient. There's an example with ridge regression. This is just a simple complication of what you saw before. So what you would have now is just an additional set of parameters with a lambda here. And then the Hessian matrix changes slightly. You would have 2 times lambda times the identity matrix. And that's the only change. And it's pretty easy to set it up again. And you don't get any more insights because you would then have simply how to say, it just as the ordinary least squares, but with now a parameter lambda, which you have to tune. So if we now summarize this, I'm just going to use this kind of summary to motivate a little bit about the what is coming now. So you will see that the gradient descent algorithm is pretty deterministic, and if it converges to a local minimum or global minimum. And in machine learning, we often deal with extremely complicated landscapes. So we may have many local minima, we may have saddle points, etc., etc. And this normally can lead to pretty poor convergence of the methods or performance. You saw also that's very sensitive to the initial conditions and the initial learning rate. And they are expensive to calculate for large data sets. So you're dealing with typically matrix or matrix vector multiplications. And these are floating point expensive. It's very sensitive to the choices of learning rates. And the other thing, when you have a constant learning rate, is that all directions, like in this case, we had 2 vectors, not 2 values of beta, which means we have 2 gradients. But since we had a constant learning rate, the way these gradients move is multiplied with the same variable. So that means that they actually are diminished or propagated through space with the same constant. So that means that the gradients are with gradient descent treats all directions in parameter space in a uniform way. And that is clearly a drawback because you may have one variable which varies a lot and other variables which barely change for iteration step by iteration step. Now, before we move on to efficient ways of calculating the gradients with stochastic gradient descent and more refined methods, there is a small addition which is worth looking at, and that's called the improving gradient descent with momentum. And I just wanted to explain to you what these momentum-based methods are. So the overarching message is that you take into account information about previous gradients. So if your gradient varies widely from one step to the next one, you try to smooth that out with information about the gradient from a previous step. And I normally like to call this momentum or momentum for memory, because you keep track of the memory from the previous iteration. This is a technique which is widely used in numerical calculations. So if you're looking at the algorithms like this Broyden's algorithm for finding the roots of a function, you will often see this kind of algorithms where you have a parameter which you multiply the previous iteration with. And that's a way to keep track of previous information. It's called momentum because it has a kind of inspiration from the solution of Newton's equations. So let me try to demystify this name momentum and then show you how easily you can actually implement it. So in the slides here, you will find this discussion about gradient descent with and without momentum. So let me just switch back to the whiteboard. So this will be gradient descent with momentum. Oops. We are still having a plane learning rate, which is just kept constant. So I like to call it memory, but I mean that's not so important actually what we call it. And let me just give you the basic mathematics behind it. So suppose you have a particle which moves in a field where you have a force. So we now take that as an example, and this is the way it was originally motivated. Particle moving in a field. So that would experience a force, which then is given by minus and then the gradient of the potential. So now you're going to see where the gradient comes in from. So you know that the force is given by the gradient of the potential, right? I hope you haven't forgotten Newtonian mechanics, right? And the famous differential equation, when you add a friction term, so you have the acceleration, and then you can have some friction or drag term, which is velocity dependent. So this is typically called a drag or friction term, etc. And this is without some kind of added potential. So if it was to move in a harmonic oscillator potential, you would have an X term. But let's now assume that this is the equation of motion, and then it's given by the gradient of the potential. So when you then discretize it, the second derivative, and this is actually the finite difference formula, which I mentioned just some instances ago. So this is given by X at the time t plus a time step delta t. And you've probably seen this formula many, many times. It's just a manipulation of the Taylor expansions. And then we have delta t squared. So this is just taking the Taylor expansions of X of t plus delta t, and so add to that one the Taylor expansion of X, now f of t plus t minus delta t. And then you can get this approximation to the second derivative. Now, this is the function. If you want to calculate the second derivative of the exponential function, and you use this function then to calculate the fourth derivative based on the results from the second derivative, you will fail miserably unless you use automatic differentiation. So these kind of formula are nice and neat to use, but they don't give you a very good accuracy. But let's just use this formula here. And then when we now go to the first derivative, we approximate that one with what's normally called Euler's forward scheme. And you've probably seen this equation many, many times. X of t divided by delta t. So I'm not going to ask you if you haven't seen it, because that would be an offense. Because I guess everybody has taken a course in numerical mathematics or computational physics or whatever. And then if we just plug it in, what we have then is an x of t plus delta t minus 2x of t plus x of t minus delta t divided by delta t squared plus this mu, and then I have multiplied with x of t plus delta t. And then you would simply define some new quantities. delta x of t plus delta t, which is given by x of t plus delta t minus x of t, not the delta t, delta x here. And then I have a delta x of t, which is x of t minus x of t minus delta t. Then, if you now look at the equations which we have, I can now rewrite the differential equation in terms of these quantities. So I just plug them in, and then I can rewrite everything as, I can separate out delta x of t plus delta t equal minus delta t squared divided by the mass plus this mu of delta t multiplied with the potential, the gradient of the potential. So I should put arrows here to indicate that this is a vector actually. And then I have plus m divided by m plus mu of delta t times delta x of t. And then I would just define delta as m divided by m plus mu of delta t. And then I define a new parameter gamma, and gamma equal delta t squared divided by m plus mu of delta t. And then I can rewrite the whole equation as x of t plus delta t is equal to minus gamma. And then I have a gradient of v of x plus this delta of delta x of t. Now, the way I like to view this, so this would now be, if you now think of this x of t, in our case, this x of t is going to be the parameter beta which we have. And then you would have x of, let's just call this x of I. And then x of t plus delta t would be your beta at iteration I plus 1. So then what you see then is that this, you could rethink this equation as a delta b of I plus 1, which is equal to a b of I plus 1 minus a beta of I. And then I know that my beta of I plus 1 is now equal to a beta of I minus a parameter gamma. And this is multiplied with a gradient. Oh, let's just write the gradient here. The gradient calculated at beta of I. And then I can rewrite this in terms of a parameter, which I'm just going to call delta of beta of I minus beta of I plus minus 1. So if you now look at what we have in this equation here, we have a term here, which we can interpret as delta beta of I plus 1. We have a gradient term here, and then we have an additional term here, which I'm just going to call the memory term. So this term here is normally called for a memory term. Or momentum term, because it's proportional in Newton's equation, is actually proportional with the momentum, which we have in Newton's equation. So that's, if you go back to Newton's equation, which we rewrote here, you would then have the acceleration term, which is this term you see here. And then this is a term now which plays the same, the one here is this, a term which plays much the same role as a momentum. And that's why when you rewrite this equation here, you normally call this either a momentum variable, or the way I prefer to call it is a memory term, because you see now that this term here depends, if you look at this term, it depends on the value which we had at the previous time step. So you see you have a new value, which is a difference between the new value minus x of t, the previous step, and then we have a previous time step here again, a t minus delta t. So you're dealing with 3 time steps. And you could think of this when you look at the equation here. So you have the new values defined in terms of the difference between the new value and the previous value. There is the gradient. And then we have a term here, which now is being interpreted the way I like to interpret this as a memory term. You actually scale it with a difference between the value x of t and the value x of t minus delta t. And you can actually rewrite your equation for the betas in terms of a similar term here. And this delta becomes just a parameter, which you can play around with. This is something which normally can speed up the calculation of the convergence of the gradient descent method. So it helps to actually gain speed in a specific direction with still a persistent but small gradient. So let's now look at some calculations here where we implement this. So let me show you how you can implement it. So the first example here is just a plane in the slides. It's just a plain gradient descent. There's nothing particular with it. The only thing which I've done is now simply so I do 30 iterations. The only thing I've done now is to calculate a very simple functions. You can see here, my objective function is x squared. And surprise, surprise, the derivative is 2 times x. So this is my gradient. And you can see now the way it converges towards the minimum. And you can see now that the gradient first is not exactly equal to 0. And then it slowly converges to 0, as you can see here. And after something like, I'd say 26, 27 iterations, to the fourth leading digit, the gradient is 0. And you can see how it approaches towards the minimum here. And we know the minimum should be at 0. It's x squared. So here I would typically then need something like 26, 27 iterations to reach the final point. Now I can speed it up with momentum. And the only thing I need to do now is to define a new variable, which I have defined here to be 0.3. So I take now my original step size, which is my learning rate. I have the gradient, and then I have momentum and multiply with the change. So I start with putting the change to 0. So my new change is given by the step size times the gradient plus the momentum times this change. And then my solution is actually the solution minus this new change. And then the change is now changed to the new value. So I keep information about the previous iteration. And you can see now the same function. After 11, 12, 13 iterations, I have actually reached convergence. So in this specific case, I've halved the number of steps I needed to reach convergence. So this is a simple, the method is extremely simple to implement. And it normally smooths out because you keep information about previous gradients. So in a sense, instead of having 2 points only, the old point and the new point, you have the old minus 1, the old one, and the new one. And then you take an average of these points. Not exactly an average, but you multiply it with a constant. This constant, which we call delta in the handwritten notes, is normally a constant you would have to tune. And that becomes a new parameter. So you see the number of parameters just going to escalate. There's always some people who get very, very disappointed with machine learning when they see this. Say, I'm just tuning parameters. But this is a cheap way of actually speeding up the convergence of a standard gradient descent. So what we see now is standard gradient descent, okay? What we're going to do next is actually to move over to stochastic gradient descent, because now we're actually calculating the full gradient. So the next step is something which is called stochastic gradient descent. And I just wanted to give you some words first. So in gradient descent, you compute the cost function and its gradient for all data points. Yeah. Yeah. Yeah, we don't know. Actually, one thing you don't know is whether you're on a local minimum or not. So the yeah, you want? Are you okay? No, I'd say, I would say if it converges fast, it's a good thing. But clearly, we don't know whether you reach a global minimum or local minimum. So you may be stuck in a local minimum, and that may not be the optimal minimum which you want to reach. And that's why people normally do stochastic gradient descent, because then you would place yourself randomly in your whole data set. And then if you're lucky, you may hit actually the global minimum. So the cases we've been looking at now, I mean, in every demonstration, you will always see the nice vanilla cases, x squared, we know the minimum, it's pretty easy to find it. But you would have to play around with different, both learning rates, momentums, and all these parameters. You will often see then people in machine learning, they would say we have used the root mean square propagation, ADAM, ADA-grad, and we found that this and this method do perform best. So there is no a priori kind of, how to say, determined type of optimization method you should use. And people tend to use actually many, and then pick the one which gives the best results. That's a pretty common practice. If you know that your function is a convex one, you would normally use a method which is called ADA-grad. If you don't know anything about your function, normally what happens is that this root mean square propagation, or ADAM, the method I mentioned yesterday with all the hundreds of thousands of citations, is normally the method which people tend using. But I would say there is no kind of a priori set of parameters and a set of methods which work best. You don't know that. Unless you have a very good insight about the function. And in linear regression and logistic regression, you know what the second derivative looks like. And that, in most cases, these are actually positive definite matrices or semi-positive definite matrices. And that means that there is a global minimum. So, but when you come to neural networks, I mean, this is a rugged surface with millions of parameters. So it's a high dimensional optimization problem. And there's always a trade-off then between how many CPU cycles you want to use and the accuracy you're willing to accept. I hope that helped a little bit, Ali. Yeah. So there are many data sets here, like this image challenge, where you have millions of examples. So it's normally wasteful to actually compute the full cost function of the entire training set in order to perform only a single parameter update. And a very common approach is actually to compute the gradient over batches, over smaller regions of the training data, but you would sum this up to the full data set. So a typical batch could contain just some 1,000 examples from an entire training set of several millions. And then this batch is then used to perform a parameter update. And in stochastic gradient descent, there are extreme cases when you have only one batch, but you place yourself randomly where you start in your data set. This approach is normally never used. So you would typically split your data set into small batches. And just to give you an example here, you could now think of you having 10 data points. And if you decide that you have 5 mini batches, then each set would contain only 2 data points. And then you could then have batch 1, batch 2, and up to batch 5, which contains these data points. Or you could shuffle these data points randomly. So you would, instead of having x1, x2, you could have picked randomly x5, and then the next one would be x6. And then the final batch here could be x1 and x2, just to give you an example. And then your gradient would now simply be the sum over all these batches here. And I'm going to show you some simple examples on how you can do that. So typically, the basic algorithm is that you would start with a given number of data points. You define a set of mini batches, and each batch here contains now, in this case, 100 divided by 5. So that contains 20 data points. No, sorry, that contains 20 batches. It has 5 data points in each batch. And then you have 20 mini batches. And normally you would repeat these calculations a given number of times. So that means that you have something which is called epochs. So that becomes a new parameter you have to play around with. So the number of batches and the number of epochs becomes a parameter which you need to study in order to figure out what is the optimal setup for that specific data set. So you may ask then, and where should I start? The driving parameters are the learning rates and the hyperparameters which you have in the regularization. These are normally the most important parameters. So many people tune these first, and then they play around with the number of epochs, number of batches, etc., etc. Momentum parameter, and when we now come to Adam and root mean square propagation, there will be even more parameters. So you're gonna love this, guys. As I said, everything here is done to circumvent the calculation of the Hessian matrix and the full calculation of the gradient. If you can calculate the Hessian matrix, you do it. There's no point in doing anything of what we're talking about now. This is tailored to cases where you have zillions of parameters, which you want to optimize. And I see that to optimize your time, I need to stop now, because now I'm running over time here. Okay, guys. So tomorrow we continue with this, and then we try to discuss the first project as well. Questions, things which are unclear. I mean, everything is in the slides here, and you will find again the handwritten notes, the videos, everything. So if you have problems with spare time, you can always watch the videos again, right? So my jokes become worse and worse as we move on. You probably noticed that, right?